talking about matter Chern Simons theories in an external magnetic field. This is the work that I am doing for a while under Siraj here, and we are almost near the end. So so here we will be considering these are the Lagrangians for the theories. Here this refers to a gauge group. This is SUNF gauge group based Chern Simons interaction at level Kf plus half Sgn Mf. Mf is the mass of this free fermion. So, this is a Lagrangian for a free fermion with Chern Simons interaction, otherwise it is free. This sign Mf is there to take into account when you integrate out this fermion, then that shifts the level of the low energy effective theory and then it will be a low energy theory will be SUNF at level Kf.
So, this is in 2 plus 1D?
Yes, this is in 2 space dimension and 1 time dimension. This is the first theory that we will be considering. We will call this regular fermion theory, and then this is the second theory in which we have a Wilson-Fisher boson which is otherwise free and it interacts with UNB Chern Simons interaction at level Kb, and these 2 levels are referring to the you can consider SUNB as UNB as SUNB times U1, and this refers to the level of U1 and SUN different separately. Now, why should we study these theories? These 2 theories are conjectured to be dual of each other, and first theory is a fermionic theory, second theory is a bosonic theory. So, this is a Bose Fermi like duality. So, these are like successors of level rank duality. Level rank duality is a kind of duality for pure Chern Simons theories, and these theories are this test of these dualities are there are various evidences at large n that I will discuss in a minute in next slide, and there are conjectures at finite n matching anomalies on both sides and so on. There are precise conjectures at finite n. So, this is one motivation for studying these theories, and the other things is that there are in large n there are various interesting dynamical features for these theories. For example, this theories has effective excitations which behave like anions, and this theories has very rich phase diagram. So, if you consider free energy and consider its phase structure, then they are very depending on your relevant parameter, they show very nice phase and phase boundaries and so on. So, this is a very rich structure, and then there are various interesting bound states. This is like if you consider this bosonic theory and if you Higgs it, then the effective descriptions will be in terms of G and W bosons, where G boson is the one that is uncharged under the unbroken gauge group. So, this G boson will effectively act like a bound state which is sort of unstable as you turn on coupling. So, it shows a very interesting bound state structure, and then lastly it has features of topological entanglement like long range entanglement because of topological nature of this pure Chern Simons theories. So, these are sort of motivations for studying these theories, and these are being studied by various authors over last 5 and 6 years.
Sorry,
yes.
Would you mind if I give you just a little feedback on your slides as we go?
Yes.
Because I may not be around to the end of your talk.
Yes.
Okay.
Just
My suggestion is, since this is the first time you're talking about the theory, maybe it's okay to give the Lagrangian once for the Chern Simons part.
I see.
It's a minor point, but just the first time, so that let's say there's somebody not well versed in the field. Okay, just one quick suggestion.
Yeah, I'll put the explicit.
You don't have to take all my suggestions, but
No. Thank you. I'll update them.
And also, sorry, you could just say that the matter is in the fundamental representation, which I assume it is, right?
Yes.
So this is the first time you're introducing.
Yes. So, both the fermion and the boson are in fundamental representation of the corresponding gauge group.
The slide is what Sandeep was saying.
Yes.
The first slide.
Okay, so I'll make more detailed. Yeah, thank you. Okay. So, here I will be describing the duality map between these theories. These duality maps are essentially based on large n calculations. So, here I am defining few quantities kappa b, which is related to Kb that appeared in the previous slide, and Nb in a particular manner, and this lambda b will play the role of a tooth coupling in these theories. If we do large N analysis, then this will be the coupling of the large N theory, which is this ratio of Nb by Kb, and similarly we can define the same thing for fermions. So the duality between these two theories is by Kb is related to Nf. So in one side the rank of the theory is relating to the level of the theory. So this is why it is like level rank kind of duality, and then the masses of the both theories are related in this precise manner. There are different other dualities of this type involving UN groups and symplectic groups, but I will not go into them. So in this talk we will essentially study these dualities in presence of external magnetic field, as I will come in a minute. So both the theories have an U1 symmetry. The SUN side has this obvious U1 symmetry that makes it UN, and the UN side has a topological U1 symmetry which comes from the Bianchi identity of the corresponding U1 part of the gauge field. So this is topological because Bianchi identity itself gives you a conservation law. So these are the two U1 symmetries on both sides. Now so here I am reviewing known results in this theory. So these theories when you stop the mass deformation, then they are conformal field theories, and on conformal manifold you can study operator spectrum. They are 3-point functions and they have been studied and they work very nicely at leading order in large N, and then you can mass deform these theories and consider S on cell S matrices, they match under the duality and in a very nice manner, and then you can put these theories on finite chemical potential and finite temperature, and then you can study these theories as and consider their partition functions, and they also agree at finite temperature. So these are sort of the known results. Now here I am coming to the main question that I am going to ask is that these theories have effective excitations which are like anions that we know. Now I am asking the question that if you turn on a background U1 gauge field, background U1 magnetic field for these U1s that we considered above, then how does these anions behave? For example, if you have spinning particles, if you put in a magnetic field, then they have an effective interaction like B dot S. So this is like free theory intuition, but how does this interacting theories behave? This is the question we will try to answer in this talk.
Can I ask you, because I should know this by now, but just roughly, because you said that the U1 which is fermion number on one side becomes the topological U1 on the bosonic side. So roughly is the duality that it exchanges the vortices on the bosonic side with the fermions? Those are dual to the fermions on the fermionic side? That's
yes, so it will be baryon monopole kind of duality. So
because you want it in terms of gauge invariant operators, I guess. Huh?
Yes.
Yeah, but what you say is absolutely right, but of course because of Chern Simons term, every vortex traps a particle. Traps particles. So it's basically particle.
So there's a bound state of
Because Chern Simons tells you that F is equal to J. So when you have an F, you have J.
And then in the monopole background you need to make suitable singlets, like putting various fundamentals together.
You know, so when this is a U1 theory, it becomes very much like what is it? When it's UN and large N, roughly you should think of it as particle. The vortex is not playing that big a role.
Okay, thank you.
Okay, so here first we will be considering non-relativistic free particles in a magnetic field. So we start off with a particle which has spin S and G is the Landau G factor, and we consider its eigenspectrum which is labeled by two numbers nu and L. Nu is the Landau level index which runs from 0 to infinity, and L is the orbital angular momentum which starts from minus nu and goes up to infinity, and energy levels depend only on nu. So L labels the degeneracy of these energy levels. This is like very much familiar for all of us, and this phi nu n are the wave functions, corresponding eigen functions for these energies. Now we will be considering an interesting releveling of this spectrum, and as you will see that as we go ahead and turn on Chern Simons interaction, this releveling will play a very crucial role. So, we are relabeling this phi nu n in terms of a newly defined function E m n such that m is nu and n is nu plus L, and because of this condition m and n runs from 0 to infinity, both of them are integers and runs from 0 to infinity. So, and here are the explicit form of these functions. I will come to these functions in a bit, like telling you what these functions are in terms of more fundamental structures. So, U is mod z square. U will be scaled version of mod z square, some scaled by magnetic field. Yes.
What was ln m minus n? That's some operator.
This quantity? Oh, so this is this Laguerre polynomial, a particular polynomial. And yes, so this is a particular polynomial, and then you have an exponential damping factor, because if your magnetic field is very high, then things get squeezed into small orbits, and this is the rotation part, the angular momentum part, and these are some normalizations suitably chosen to make them orthonormal. These functions has very nice symmetry properties. We will come to them. I'll come to them in details, like what these functions are, why we are doing.
And just to understand your notation, what is little b?
Little b is the magnetic field.
And
Capital M is the mass of the non-relativistic particle, and we are assuming B to be positive.
That's a usual cyclotron frequency.
Usual cyclotron frequency. This will be the frequency.
Okay, very good.
So that's the harmonic oscillator.
Yeah.
This is the harmonic oscillator, and this is the B dot S interaction. And we will assume particular sign of B that does not lose anything, because you can do a parity flip to get the other sign. Now we want to see the propagator for this free field. This propagator is denoted by this quantity alpha, which depends on 2 points x and x prime, and this is the differential operator, gives you a delta function. We want to solve this equation. First thing we note about this equation is that it is not a translational invariant operator. Because of this interaction, this AI is the gauge field because of the background magnetic field. So, this alpha that is defined in this equation is not supposed to be translational invariant. We are working, so the point is that we are working in a magnetic field which is uniform and perpendicular to the plane, and this magnetic field, suppose you choose a gauge which preserves rotation, then it breaks both the translations on the plane. Or if you choose a gauge in which you preserve one of the translations on the plane, it breaks the rotation and the other translation. So, there is no gauge in which the symmetry of the physical problem, which has this both the symmetries, like translation on both the directions of the plane, these are like symmetries of the problem, like you do not have any particular choice of gauge which preserves both these isometries. So, this is a technical problem. So, this is the problem that we are dealing with here, that this A is not preserving the symmetries. So, what we will be doing is the following. We will say that suppose we are working in gauge 1, then we can do a gauge transformation that changes my propagators in a precise way, because I know the charge of the fermions. Then if I make a gauge transformation, it will become propagator in another gauge, but in the other gauge we expect it to be preserving a different isometry. So, this is like a word identity. Suppose you have an answer in rotational gauge, you do a gauge transformation, you get an answer in a gauge in which you preserve translation in x direction, but this is not automatic. So, that gives you a condition on what kind of function that you have to have in rotational invariant gauge. So, in particular you have two word identities for two translations if you are working in rotational gauge. By rotational gauge, like the gauge in which you preserve the rotation on the two plane. So, this word identity can be solved, and solved in the following way, where the propagator between 2 points x and y is written in terms of a known phase times a function alpha r is for reduced, which is now preserving all the isometries. It is rotational invariant because we are working in rotational invariant gauge, and because we solved the word identities, it is now translationally invariant on both the directions. So, this quantity has all the symmetries if the magnetic field, suppose you are trying to solve this problem when there is no magnetic field, then you will have all these three isometries, and they are still present in this reduced propagator. So, this is how we will deal with it. So, at the technical level, this phase will essentially turn into this non-gauge non-translationally invariant part into a translational invariant quantity, and then you will have this satisfying a translational invariant differential equation. So, this is now we proceed forward to solve for alpha r.
So, that exponent was just x, the vector x cross vector y whole thing dot the z. Right?
Z.
But
So
note that there are 1 2s all over the place.
See the past this is like an antisymmetric,
But dot z, z hat.
No,
It's
x1 is for
it is the angle between the vectors. You have x vector, you have y vector,
Okay. Right.
it is the angle between, because you see you have solved for both the word identities, and what is left is supposed to be rotationally invariant.
But I think he's right. No, if you take the vector x which has components x1, x2, y which has components y1, y2, take the cross product.
Yes. So, it will be epsilon ij times xi yj, that is what it is.
And the
It's the-
magnitude of the z vector is basically magnetic.
Yeah, z is your coordinate on the plane. Yes.
What is the differential equation solved by alpha?
Yes, so alpha, I am coming to alpha here. So, alpha will essentially solve the same equation in which this a will replace by ax will get replaced by ax minus x prime. So, ax is a linear function of x in this gauge.
Which gauge
We are working in rotational invariant gauge, in which ax is a linear function of x, and because of this phase it will change into ax minus x prime, and then this operator becomes a translational invariant operator. Okay, now we come to solving for this reduced propagator, which we work in the time direction in momentum space, which is this frequency omega, and we will continue working in position space in the plane. So, this is a Fourier transform in time direction, and we can solve this equation, this differential equation, by plugging this expression in and then using the orthonormality and completeness of the wave function. So, we know the eigen functions of this operator we studied little bit ago, we can just use it to solve it like this. So, this is the expression of the propagator. Note one thing, left hand side is a function of x minus y, whereas right hand side is at two different points x and y. What it says is that one can actually set y equal to 0 on the left hand side, we are not losing any information because this is a translational invariant function. We can set y equal to 0 on the right hand side, and then because y equal to 0 is the origin, then only those terms will survive which are non-singular at the origin, in particular the ones that are not rotating. So, if we set y to 0, if we set y to 0 in this expression, then only L equal to 0 contribution will survive. So, that simplifies this quantity, or in other words, if you separate this and then there should be a sum over nu and L, both of them.
L is in the numerator.
L is in the numerator. So, in other words, the sum over L in above makes it a translational invariant quantity.
It's intuitive, right? I mean, each individual wave function is not translational invariant, but the combination of everything in the general scene.
But what happens to non-zero L at origin? It becomes 0?
Yeah, so from the explicit form of the wave functions you can see they are becoming 0. It will become 0 because there are certain factors of u in front. So, they will make it to 0 in some sense.
Anything with the angular momentum m has e to the power I m phi, and then to be analytic has to have a factor of r to the power n at least.
Otherwise, they will be singular at the origin.
Think of it in terms of the cyclotron orbits semi-classically. We have cyclotron orbits scattered all over the plane, and just translating everything using this magnetic translation.
Yeah, this translational symmetry of the center will be the degeneracy.
And then we are just averaging over them.
Yes,
Right.
in some sense, yes.
Right.
So translation variance is not broken down to a discrete subgroup. Right?
No, translational invariance is present in the physics problem. You have a magnetic field perpendicular to the plane, it is not breaking your translational invariance, that is there. It was the gauge which was creating the trouble.
Because in the usual Landau level calculation, these translation vectors become non-commutative. Right? Because of
Yes, in that way you can think, yes, center of mass coordinates non-commutative. So, we will see a version of non-commutativity here soon. So, this we will come to this, we will come to this.
But so far you have been talking about ordinary abelian translations.
Yes, simple translations on the plane which commute abelian part, yes. So, the point of all this exercise is that we will get familiar with these new functions which will have very nice properties soon it is coming soon. And what we get is that this propagator, reduced propagator can be written in this nice fashion. Few things is that first thing is that this is a Lorentz scalar. So, whenever we have ENN, that does not have a phase. So, because this is a Lorentz scalar, only these quantities appear here, not like ENN plus 1.
Lorentz scalar, you do non-relativistic, right? Just to make sure.
Yes, you can think, then talk about rotationally scalar.
Oh, okay. So what alpha r is rotationally invariant. That's what you're saying? Huh?
Yes, alpha r is rotationally invariant.
Okay, got it.
For example, if you had a fermionic propagator, that will have some, that will become a matrix and various components will have spin. And
This is a rotationally invariant function of omega and x, or just x in the rotationally invariant in the 2D plane.
yes, yes,
So therefore it's ENN. You're saying.
yes.
That's why it picks out angular momentum 0 basically.
Got it. Okay.
Okay. So, now we turn to the problem of relativistic free scalar field in the magnetic field. Now, this is it satisfies the Klein-Gordon equation, which is basically the same Hamiltonian that you had in the non-relativistic physics. So, you can solve this equation in a similar manner and you get this answer. Answer m square, this is now this quantity m square enters in this manner, these are the poles at different energies, and you can do you can take the usual non-relativistic limit by setting omega is this and taking mass to be large, and you can recover the earlier propagator. Yeah.
But with s equals 0. The earlier propagator at 0 s.
Yes, 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 0 spin. So, propagator, yes, propagator got contributions only from those, right?
I think it's talking about the particle having spins.
Yeah, so that depends on, see here I have not coupled any b dot s term.
Because there is no s.
Yes, there is no s, so you will recover the spinless non-relativistic particle from this. Yes.
I guess the frequency for the extreme relativistic case where m is 0, omega goes like square root of b, right? That's the
Yes,
standard.
yes. Okay. Now we turn to Dirac fermions in the magnetic field. So again the spectrum is given by a formula like this, where this nu, sorry, this is eta. Then this eta tells you if you are in positive energy state or negative energy state, and then there is this nu, which is the Landau level number, just like previous time, and then we have a coupling here, which is the analog of b dot s coupling. So sin mf by 2 is supposed to be the spin of this interaction in 2 plus 1D. So, if you look at representation theory of SO2, 1, then we have a non-trivial invariant, which is epsilon mu nu rho m mu nu p rho, where this is the angular momentum generator, this is the translation generator. So, because of this invariant, when you give a particular sign of the mass to the fermion, it picks up a particular sign. This is a speciality about 2 plus 1 dimension. So, this quantity here sin mf by 2 is the spin of the fermion, and this is b dot s coupling, where Landau effector is 2.
And sorry, just one, eta takes value plus or minus 1.
Plus 1 or minus 1 corresponding to positive energy state and negative energy state. So, this is this particular energy spectrum, where L is again the orbital angular momentum of the particle, and this we give a particular name, which we will be using this symbol. So,
And I used to know this once about, but I'm a bit confused now. If you take the extreme relativistic limit, set mf to 0, then there are some 0 modes, right?
yes, yes,
There
yes.
is one sort of
There will be exactly 1 0 mode.
1 0 mode.
in this example, yes. We will come to this in very quickly,
At modulus of NF, and that goes to 0.
which will just come
One
in.
of the two spins, right?
Yes.
Well, either positive energy.
Exactly. That's what I wanted to do. Is either positive or negative. No? Yeah. Okay.
Yes. For example, if sin MF is positive, then it will be a pole at positive mod MF. Now, if you take, so it is a positive energy, but if you take MF to 0, then it will go to the origin. We come to this in next slide.
Yeah, this is just wanted to say because it's slightly tricky or whatever. I mean, you get one.
Yeah, so, yeah, so we will come. We are coming to that. We are coming to that. So then you have these wave functions, which is this column vectors, and again you can take non-relativistic limit of this wave function of the Dirac equation, and you can get non-relativistic spectrum that we studied earlier. Depending on your sign of eta and sign of MF, you will get suitable wave functions, which will either be psi upper component or psi lower component. So this is a story. Now we come to this point. Very important point is that because of the spin, the spectrum of energies is not totally symmetric between positive and positive part and negative part. So there this E going to minus A symmetry is broken, generically broken, but if you set M to 0, then that will be restored. So this is related to various anomalies in 2+1 dimension, but we are not going to into that discussion. But we make this particular observation. This was the positive energy states and these are the negative energy states, but they have this particular relation that one of them is related to the other by a shift of the level nu. So what you can do, you can choose nu carefully in this particular way in terms of a new variable n, such that both of them agree. So for every n, if you choose nu for positive energy state by the first formula and nu for the negative energy state by the second formula, then they will have same magnitude. So this is the part of the spectrum which is symmetric in positive and negative energy states. Now note one thing, suppose sign of MF is positive. In this case n equal to 0 corresponds to nu equal to 1, but we already know that nu ran from 0 to infinity. Therefore, nu equal to 0 state in this particular case will be left behind from this spectrum. So that will be this floating state. So if MF is positive, then this is a positive energy state which is floating outside. So by floating I mean this is not the part of the symmetric spectrum, and correspondingly for negative MF.
Shifting the origin to that state?
No, we are not shifting. So I am saying that the spectrum should be considered as this is, let us say, 0. If MF is greater than 0, this is the special state, and then you have symmetric. And this has the magnitude mod MF. So if you set mod MF to 0, then it goes to the origin, but otherwise it is somewhere either above or down, which we will call be exceptional level, which will play a very important role. Okay. So this is the spectrum for the theory. Now we turn to calculate the Green's function in this theory. Again, this is like this is the lemon representation. So we can just solve this equation using Fourier transformation, using the orthonormality and completeness of the wave functions, and this solution takes this particular form. This gamma 3 appears because this, from Dirac equation writing it into Schrodinger equation, you need to multiply by an operator which is gamma 3, which comes with time. So because of that it looks like this. It has poles at this positive and negative energy states, and these are the wave functions are the residues. And we have already seen one thing that we can immediately do is to set x prime to 0. That simplifies quite a lot, because again the only 0 angular momentum states will contribute. So this is first simplification. Second, we have noticed that there is a part of the spectrum which is symmetric between positive and negative energy states. So in this sum we can in particular combine these two states. So we are doing that, we are combining them, and I am presenting a result after all these things are done. Alpha F is for free, R is for reduced, and plus is because it multiplies gamma plus. So we are considering fermions. So the 2-point function is a 2×2 matrix, which can be written in terms of gamma plus, gamma minus, gamma 3, and identity times alpha identity. and I am presenting here formula for all these different components. Now, these components are again written in terms of this functions E n m. See, there is a shift because there is a charge associated to it. So, this takes care of the charge, and this pi omega n is a polynomial in omega, which has these two poles that we combine, positive energy states and negative energy states, that we combine to get this expression. So, this expression for this pi is given here, which is exactly those poles. Now, I have presented the formula for plus. Minus is obtained by taking complex conjugation because of Hermitianity of the fermions. And then I have presented a formula for identity. Now, identity and 3 are related very closely by just changing the sign to be with plus. So, this
is identity pi. Pi is identity?
Pi, no, pi is the
Oh, is the
denominator.
Sorry, so this is plus, then there, so that is identity, and where is the 3?
Yes, so 3 will have an expression like this, only except that this will become plus, and 3 and identity has only ENNs because of charge conservation. So, this is the structure of the free fermion propagator. Now, this looks like complicated, but it has a very nice simple form. Like we can invent some operations, some algebraic operations, with which this will become inverse of a very simple quantity, inverse of a very simple operator in some sense. So, we will come to that. So, first is that all these things can be written very nicely in terms of ENNs. This is the first observation. Second observation is that the spectrum, this has poles only at this particular values, which even with spin half gets poles only shifted by B dot S coupling, otherwise it was like free theory. So, these are some observations we make at this point. Now, here we ask the question, suppose there is a particle of spin S, a relativistic particle of spin S, then can you write down the propagator? If there exists one, then can you write it down, like if it is free relativistic particle of spin S, then you make a very obvious guess, okay, so these are the poles of the propagator, this is the effective mass of the particle, this is the free part, free bosonic part, and this is the coupling G dot S, this is the coupling with the interaction. So, this will be a very naive guess for the answer for free particle of spin S. Now, it turns out that, so in this talk we ask this question, that what happens to the anions. So, we will be studying these theories at leading order in large N, but all order in toothed coupling lambda f. Lambda f is a toothed coupling for these theories, and we will find the 2-point function in this particular regime, and 2-point function will only have poles, and those poles will be exactly given by this formula, where spin S is given here. This spin S is the effective spin of the particle in the following sense. So, it has two parts, as you can see, first part is mf by 2. This was the part that was present in the fermions. So, this was free fermion contribution, and there is a correction because of lambda f. So, this correction due to lambda f could be understood from just representation theory of these fermions. So, these fermions that we considered, these fermions are in fundamental representation for Chern Simons theory. So, because of interaction with Chern Simons theory, they will get a effective spin. This is like the dimensions that you get in Schwinger construction, like C2R by kappa. C2R is the quadratic Casimir of the representation R, and kappa will be this level K. So, this can be made precise. For example, if you take these fermions on a unit sphere and take non-relativistic limit, you write down the theory coupled with Chern Simons matter, take the non-relativistic limit of this theory for fermions, you will see that the spin connection that you have on the sphere effectively gets this shift because of coupling to Chern Simons. This can be made precise.
Maybe you can say that there's a long overdue paper with Naveen and many
Yeah,
others
yeah,
which we're making all this very precise.
Yes, we are making that very precise. So, then
I'm sorry, your conventions lambda goes from 0 to 1?
0 to 1. So, first thing is about the sign. So, there are various things we will make an observation about this quantity. First thing, note if sign of mf and sign of lambda f are same, In this particular case, at lambda f equal to 1, you get spin 0. So, this is like when these signs are same, the sign of MF and sign of lambda f is 0, you expect at strong coupling you get a bosonic excitation which has spin 0. Whereas, if these signs are of opposite nature, then at strong coupling like mod lambda f equal to 1, you get effective spin either plus 1 or minus 1. This says that if you take this theory in the strong coupling, it is dual to a vector like theory. So, in particular what it is saying from our old experiences, we have seen that sign of MF times lambda f, when this is positive, then the theory is dual to a regular critical boson theory in which there is no condensation. So, the effective excitations are bosonic objects which are spin 0, which matches with this prediction. And on the other hand, in recent works we have seen when the sign is opposite, the theory that corresponds to essentially condensing the theory. In our duality map we have checked that, okay, in the duality map we have checked the relation between masses of the theories. So, in this particular sign you will see that the mass of the effective Wilson-Fisher theory is negative, which leads to condensation. So, because of condensation, effective excitations are W and Z bosons, and you can also show that Z bosons are in the leading order is much more massive compared to W bosons. So, it is an effective theory of W bosons which are vector like particles. So, this is very much consistent with this picture. So, this is what we are going to find after all the calculation.
But you are, just to understand, you are going to do the many body problem, right? That
Yes.
You will do the problem in field theory, right?
We will do
It
that.
won't be one particle put in a magnetic field.
No, we will do a proper field theory calculation and calculate the propagator, and after the calculation we will see it has only poles. So, it is an output.
That means there is a single particle.
Yes, so effectively these are like single particles with some renormalized mass. Yes, with the change, with effective spin given by this formula and some effective mass C, which will be determined by the interaction with the magnetic field. So, effectively that will be the final story.
And maybe you can say that within the broadened Landau levels, we're not sure that that is the story.
Yes, so what will happen is that when we have free, so when we are in free theory, then we had all these Landau levels which are highly degenerate. Now,
Sorry, I was going to ask that, but so then therefore there's also the issue of the chemical potential. But here you are describing with mu equal to 0.
yes, so here we are considering the theory when we have not filled anything. I'll describe.
Isn't it, sorry,
Yes.
isn't it strange? I mean, you actually have very sharply defined poles with no width.
Yes, we have.
Is that a large N concept?
It's a large N.
Large N concept.
It's a larger thing. It's the kind of thing Kedar saw in his thesis. The scattering next order is next order.
For N, for
From S matrix we can see this order 1 by n.
Sorry.
Yeah, so I'll make it precise in which condition this is exactly true. I'll make it precise as we go along. Yeah, so
And then, sorry, since you said it, and what is the story with the chemical potential then? You see, if you start on the fermionic side, you get a Fermi surface to begin with?
Well, there are these magnetic fields.
And then you have a magnetic field in that which splits it. I mean,
Yeah, so it's a pretty story. I'll say, I'll just say, okay. Okay. It's, the chemical potential can be, the Landau levels will get broadened out. Okay, the Landau levels, which in the free theory at one energy, will get broadened out as you keep piling electrons in, they get broadened. Now, if your chemical potential is between the broadened levels,
So they get broadened because that's like the forward scattering effect of the interaction.
they get broadened because the energy to put the last electron
Yeah.
will be more than
Right. So
the
the
energy to put the first.
energy will depend on the occupations.
Exactly.
Yeah. So like forward scattering.
That's what it's
Like Fermi liquid case. Energy depends on occupation numbers.
Right.
Yes.
Right.
we will have other
It's not
situations
scattering as
also.
such, but energy
Exactly.
depends on occupation.
Exactly. So some mean field kind of
Yes.
kind of thing. Yeah.
That's what happens in that.
That's what happens in larger, right? So the Landau levels will get broadened out, and precisely within one of these broadened Landau levels, you'll see there's a technical issue that arises in this problem. So I think that there's a chance that there's something interesting going on here. But when your chemical potential is outside, then this is precise.
Outside below.
Outside below or above.
There's a gap to adding part.
Yeah.
Then it's precise what happens.
Then it's precise and maybe precise also inside, but I suspect that the larger expansion. And we can get into these.
I see.
So inside it's going to be gapless. To add a particle will require infinitesimal energy.
At least naively. But you know, at 1/3 filling, maybe there's an effective gap.
Gaps can open up.
There's something maybe very interesting going on there.
So this is the relevant system for fractional.
Yeah, but where you are between. Yeah, that's.
So when one says
some analog to fractional quantum Moyal gaps in your large set calculation.
Well, our calculation doesn't have it at least now, and maybe it will never have.
But you're saying in 1 over n.
But you'll see, we can surround with the problem.
I see.
And what happens in between? I'm sorry.
No. Yeah, so we will come to these points in the last part of the talk, sort of. So, you know, and this broadening out will also have certain cases in which this will happen. There are certain things we will come to this.
Maybe the part of the talk that Kedar may not be there for.
Oh, okay. So I can summarize the talk like quickly.
No, just go. You're good.
Okay, so with these things in mind, we come to turning on the Chern Simons coupling and the interaction. So earlier we were solving this equation for the 2-point function. This was the free Dirac operator, and this is the 2-point function. This is the delta function. Now we have got an extra piece here. This sigma is supposed to be the self energy due to interaction with the Chern Simons theory, and it couples to alpha like this. This is the Schwinger Dyson equation that you get working in a particular gauge. We are working in the gauge in which A minus of the gauge field is set to 0. This gauge is very useful in solving these equations because it gets rid of certain interactions between Chern Simons gauge field among themselves. So, we will be working in this particular gauge. This is the first Schwinger Dyson equation, and then this equation closes like sigma is given in terms of alpha. So, these two equations together sets the Schwinger Dyson equations which we want to solve. So, this was the story when you have Chern Simons interaction turned on. Now, first thing that we say the magnetic field is 0 for the time being, then this gauge covariant derivatives will be normal derivatives, simple derivatives, and then we will have translational invariance. So, here I am giving you a counting why these equations are sort of solvable. So, we have 3 translational invariants along 3 directions, and from this equation it can be argued that this quantity sigma has a very trivial time dependence, because you see this equation here, propagator is independent of time apart from this delta function in time. That makes this whole equation dependent only on delta function in time. So, time dependence is completely known for sigma. So, now you had 3 translational invariants, 1 time independence, and we have this rotational invariance. We are working in the gauge in which we are preserving rotation. So, this is 5 symmetries you have, and all the problem was dependent on 6 parameters because x has 3 components and y has 6 components. So, effectively 1 parameter family of non-trivial equations that you are supposed to get. And what you will get, because these are integrations, you will get integral equations, non-linear integral equations in 1 variable, and then you solve them. That's the.
Just so I make sure, sorry, when you say 3 time translational invariances, meaning including time? No, I didn't understand.
Yes.
Including time.
Including time.
Fine. Okay.
So, but we have
Because
time
you-
independent plus one also, right?
So then,
So-
what is the additional time?
Yes, there will be
Confused.
translational invariance in say center of mass frame and relative time independence. So, first argument was for the
Okay.
let us say
I see. Center of mass and then in addition the relative.
yes, because this guy is the relative one.
That's what you're saying. Sorry. Okay, I got it.
You see x minus y. So, we had 3 total killing isometries,
Got it.
1 rotation and 1 for relative time.
Neither of the propagator was not a function of time either in x or in y.
That's what it's saying. Got it. Okay.
I mean sigma was.
So, it became 1 parameter family of equations. although non-linear, but that got solved. You are a part of it. Everyone is a part of like Siraj, you and Spenta, many Sachin, all of them. I don't want to repeat.
Make sure when you give the talk outside, you mention us prominently.
I will. In the first slide, I have not spent any time, so there every name is there.
Go ahead. Yes.
Okay, so this was when the magnetic field was 0. Now I want to see what are the changes with the magnetic field. First change is that this gauge covariant derivative, this becomes a gauge covariant derivative. Now it has a magnetic field, but we are not scared of that. We solve this equation with the magnetic field, but this is a non-trivial part of the interaction. So we are turning to this problem, how to deal with the interaction. So first thing is that we have this trivial problem that this is not translationally invariant, but we know how to solve this using the word identities. Again, that fixed alpha to be translationally symmetric with this phase.
Can you say again why is it that it's time independent?
Relative time independence. Okay, let's look at this propagator here. This propagator at x is dependent on time only through this delta function, delta of x3, right. So now look at this equation, it is x minus y, so it will be delta of time of x minus time of y, and because of that you can set time of x minus time of y 0 here because it is a delta function.
So the only time dependence on the right hand side is the delta function. So it's not time dependent, it's proportional to delta function. In omega space it means it's omega.
So it is a trivial time dependence, like known time dependence, and then it involves only equal time propagator here. So now if you go into frequency space, neither this will have a omega is the relative frequency. So there is total translational invariance and relative. So omega is dual to the relative time.
You started with the Lorentz invariant system, right?
Yes.
Then how was
So we had Lorentz invariant theory, we put a magnetic field that puts a direction special,
yeah,
right.
but that can be tuned to 0 and suddenly you recover the thing.
Sorry.
How can it be so trivial in time? This is because it's a gauge dependent quantity.
See, this is a statement of gauge. Suppose we are working in a gauge in which A minus is 0. Therefore, this has only del x plus. If we are working in A 0 equal to 0 gauge, then it would have been x 0 here.
The whole propagator is gauge dependent, but the poles of the propagator are not. They're visible. So that's the output.
Yes. Sort of this is like on cell part of the propagator poles. Okay, so this is what it is. Now with magnetic field we are trying to deal with this equation. Here we look at this equation, which is a familiar equation we have already considered. This is the reduced propagator, this is the known phase, and we want to plug this structure back into these equations. Now using the same gauge invariance argument, sigma also has the similar structure, like sigma is written in terms of sigma reduced and a phase. Just gauge invariance tells you, this is like totally general, it does not care about this particular theory under consideration. You know what alpha is in terms of psi and psi bar, you know their gauge transformation properties, therefore you know gauge transformation properties of alpha, and once you know gauge transformation properties of alpha, you just put these word identities and try to solve them. This is like, this does not depend on this particular theory, this statement, and we expect this structure to go through in more general theories, although we do not have anything important to say at this moment. But yeah, so this is general. Now we have this expression for alpha and sigma, and we put it back in the old equation. So first thing that it does is that it makes this operator translational invariant. That happened even in the free theory, but this is the interaction part. Here something nice happens. Earlier what we had was a convolution, usual convolution in position space. Once you have taken translational invariance into account, total translational invariance into account in magnetic field equal to 0 case, then this would have been a convolution in position space between sigma and alpha. In momentum space it was a product, usual product. Now what happens due to the magnetic field is that this changes into a twisted convolution. This twisted convolution I will come into in a moment. Twisted convolution is dual to a non-commutative product in the momentum space. I will define all these things. In particular, I want to just note that this quantities has a very nice formal structure, and it turns out that we first of all we wrote solutions for the free part in terms of some quantity EMNs. It turns out that the EMNs has very nice property under this particular product here, particular convolution here. So, this is the key point for solving these equations. The functions which are common to both these parts, both the parts has nice properties under this function. We will exploit that and solve this. This is roughly the structure of arguments. So, now I am going to say few words about what this quantity is and how to deal with it. So, first here is a definition for this quantity. A and B are two functions on the space part vector x. This is usual convolution between A and B with a kernel, with a phase. This is this quantity which I will call twisted convolution, and this quantity is very famous. It's because it's used in all these papers, in non-commutative soliton papers, and here are the names. I have not missed, I mean I hope I have not missed.
Actually, I really shouldn't be there anyway.
You had a paper which I do not
It's
understand.
so
what-
insignificant, you should take it out anyway.
And the non-commutative product, there was work on it 20 years before we started working on it. That's it.
Yeah, this paper you are talking about, right?
No, I'm saying 20 years before that as well.
That your paper is pretty
It's
significant.
1986, I guess. Anyway, okay. So let me review this. Let me review it little bit. So we have this position space where we have defined this twisted convolution, and then we can go to the Fourier space and ask what is this, because if there was no phase, then it is supposed to be a product. Now you have this phase. What happens to this product? The answer is that it still remains a product, but a product which is non-commutative, but it's associative, which is given here. So you have two functions phi 1 and phi 2 at position at momentum q, and you want to define their product at momentum q. This is supposed to be done by this, which is supposed to be, it's sort of like, you know, this B can be imagined to be h bar in some sense. H bar is the, you know, h bar is Planck's constant, and this has very nice relation with ordering of operators. If you have operators and if you want to make them in a nice symmetric while ordered, then these things will be used in a suitable manner. And the statement is that if you Fourier transform this product, then it becomes a convolution in the other space. This is the connection between these two things.
Just sorry, I remember it in momentum, but there in terms of x's, is it actually epsilon ij xi minus w
This one?
I times wj? Yeah.
Yes.
And then you can just drop the wi part from there from antisymmetry or what?
No. Sorry. Yes. So this is a particular antisymmetric quantity, which is given by epsilon ij, I is xi minus wi, and j is contracting with wj. This is wj.
Right.
So this is a particular antisymmetric form.
Right.
In general, in any even dimensional space, we could have considered more general antisymmetric kernel theta mu nu, which is antisymmetric between mu and nu.
No, but I think Sandeep's right, that the omega I, omega j part is trivial.
Is trivial, right? I mean, it's just be zero.
This part, yeah, that is 0.
Okay.
But-
Just making sure you wrote it for some reason, I guess, to keep some symmetries.
Yeah, x minus w. Yeah, I would have,
Sorry, I didn't understand the question. Yes, this part is trivial.
he said you could have written more simply, just
Yes.
written xi minus.
Xi times wj, that you can do because of antisymmetry. That is true whenever you have antisymmetric kernel, you can do this. So theta mu nu is slightly more general version of it, but in 2 dimension everything will be proportional to epsilon ij. So this is no new thing. Okay, so now we looked at twisted convolutions and they are related with star products. So star products are very much useful for while ordering. So they have some nice relation with operators. So here we are exploring their relation with operators. Suppose you have two operators q mu and q nu, whose commutator is given by this anti-commuting form omega mu nu. Then you can define following functions. Suppose you have a function f of q, you take its Fourier transform, but to get the function back you Fourier transform with the operator here. So in this way you associate an operator with every function. Take the function, make a Fourier transform, but to come back you insert the operator. So this is how you associate operators with functions, and this association has a nice property that if for functions this is true that if twisted convolution G is H, then corresponding operators are just natural operator products. So, in the operator space, this complicated object, this twisted convolution becomes just an product. So, this will be very helpful in building all these things, because we know various things about operators that will translate into various identities into functions, which we do in the next slide. So, now now what we are asking is that can we build a very nice basis on this plane? We have to work on the plane. What is a very nice canonical basis? We have already seen that EMN is very nice for the free part, but here I am going to say that this is very nice for the interacting part as well, for the following reason. We defined this operator Q mu hat in the last slide.
Just one second.
Yes.
You go back again. What was Q hat? So that is in general. Okay.
That was in general.
Okay.
So, in general what you can do for, so now we are specializing to this particular phase,
Okay.
in which we have a magnetic field, and just to get standard commutation of A and A dagger,
Yeah.
we just scale them with square root b, but square root b comes downstairs. This is important. This will be important in various. So for example, in this language you can see b going to 0 limit is bit singular, which you sort of expect, because when magnetic field was not there, then the spectrum was continuous. But when you put magnetic field, tiny bit of magnetic field, they become discrete. So this is not a very continuous change. So in this language what will happen is that non-zero magnetic field will be very systematic, but taking b going to 0 limit you have to be careful. You need to do things in a careful manner.
Indranil, just one time comment. It's 1 hour 5 minutes, just so that you know.
Oh, okay.
It was a mini questions more
Yeah,
than but yeah.
Okay. So we defined this canonical A dagger, and we can build this basis of operators in this plane. This is like Z's. This is like Z's. So you can create this operator which is state M and N, harmonic oscillator state, which is this form, but then you can associate functions with them because of the previous slide, and those functions are EMNs. It turns out to be these are EMNs. So we have seen that the interaction part has an interesting product, and those products suggested are to use a particular basis of function which are EMNs, and it turns out that this same basis of functions is nice for the free theory. This is the key to solvability.
And this was in fact the basis of functions we used in the non-commutative software.
Yes, yes. This is the basis. This is used in all these places. So here I am presenting two identities for these functions. These identities are coming from the operators. See, the first one is saying that NP and P prime M is a delta function between P prime and E n m. This is the identity. If you take
Can I just ask you something?
Yes.
So, I mean, are you saying that if I take either, just suppose I take the non-relativistic problem, single particle in a magnetic field, then that has, a Landau levels which are basically harmonic oscillator levels.
yes,
I can define an A and A dagger using X and P.
yes, yes, yes.
How are your A hats related to? I'm just trying to ask. I mean, now your stuff is also in X and P, right? In X1 and X2.
In X, it's to be specific in momentum. Yes, momentum space. It's a flipped version of solitons papers.
I see.
So the start products are in momentum space and twisted convolutions are in position space.
I see. So the operators in terms, I mean, you said that you have this convolution.
Yes.
The convolution was basically because of this phase factor you got, right?
Yes, yes, yes.
This x1 and xy2 minus
Yes,
whatever,
yes,
right?
yes.
These operators, or maybe I should wait. I mean, I'm trying to understand. These operators are in terms of momenta. The operators in terms of which your convolution equations will become operator equations.
Mm-hmm.
Those operators are what? They are the positions, the momenta of the.
They will be the momentum space operator version.
Okay.
So if you go in the momentum space, and if you take every coordinate and make them non-commutative.
Okay. So do a Fourier transform of all of them, then promote those guys to operators.
Yes.
Okay, I understand. All right, fine.
Those will be the magnetic translations, right? The Q mu hats.
I tried to understand this relation, but I couldn't make it very precise. The relation with center of mass frame, right? Center of mass positions has a non-trivial commutator. I tried to make this precise. I don't have a very clean understanding. But I couldn't make it very, like we couldn't make it very precise, but we need to understand this. We don't understand it very clearly in some sense. Yeah. Yeah. So here I am presenting two identity for the functions. The identities are from the corresponding operators. So the first ENP is this operator, and then this star product is putting another operator in the operator language. So it's basically this, which we all know that this is proportional to P prime n m, which is this first identity, delta P prime E n m. Now second one is the resolution of identity. Identity can be written as sum over n n, which is the second one. So these are two identities that directly follows from the algebra of the operators, and we will use these identities. In particular, we will use them to define inverse of functions. So we have defined product. We could ask, is there an inverse, and if it exists, is it unique? These kind of questions we will be needing. We will need to answer these questions. So in addition to this, these ENMs are also orthonormal because they are wave functions in certain Sturm-Liouville problems, certain states. So they are orthonormal. So we use these properties.
These wave functions are also related to monopole spherical harmonics.
These quantities are supposed to be related to them, yes, but they are on sphere, right? I am doing on the plane, so I don't know exact mapping.
Center of the sphere, then the magnetic field is uniform on the sphere.
Yes, projective coordinates.
So
Yes.
do conformal mapping to the sphere, then
Yes, it should be sort of, but I am not sure. I have not checked their relation very carefully, like if they are monopole spherical harmonics or not. Yeah, where is the monopole sort of? I have to check. I don't know how to think about them in terms of monopole. Yeah. Okay, so we are going to use this basis. We did this Fourier transform, went to the frequency space, taking the propagator and the self energy, expanding them in first in matrices, and then each function multiplying these matrices are expanded in these basis functions, EMNs, and this charge conservation sets them to be like m plus 1, these kind of things, like these are all forced. Now what we can do is that the first equation that we had, what happened? Yeah, so the first equation that we had, which was this differential operator and the star product, that was my first equation. I want to rewrite that equation in a manner so that we can solve it using this, using these operations. So here I am defining a quantity Kr, which is the free part times an interacting part. For free part I have given an explicit expression here. What is this free part? Free part has the following property: whenever you take a function f and act with this free differential operator, this is equivalent to taking the same function f and star convoluting with this free kernel that I have written here. So we know the free differential operator, and we also know that when it acts on the free propagator, it gives you an identity. Using this, it can be shown that when this operator acts on any function, any matrix valued function f, that is equivalent to taking the same function and doing a star convolution with an object which I am calling KFR. So it is like trading the differential operator for a star convolution. The point of this is that the other part of the equation was a star convolution. So first part of the equation was an operator acting on alpha, and second part was a star convolution between alpha and sigma. This was the structure of the equation. So what we are doing is that we are taking this part and replacing this part with something star convolution with alpha, so that the whole equation has the same structure.
It's just, sorry, I just don't have the intuition. It's always possible to replace a differential operator like that with a star convolution. I mean, you go to momentum space, you say, I don't know the intuition. Anyway.
So yeah, so I'll tell you how if this operator has a unique inverse, let me assume that. If it has a unique inverse, then what you will do is that you can, okay, so suppose this operator is D. Suppose this operator is D and you have an action, oh sorry, let me write down the operator D in action alpha and gives you an identity which is like delta function. Suppose you have this equation. Suppose there also exists a kernel K such that this is true. Suppose this is true, then what will you write from here? You will write alpha is K inverse. This inverse is supposed to be defined with respect to this operation, but we already know from this equation how to solve it. This is the alpha is D inverse. So, we have an explicit expression for K inverse. So, K inverse, this first inverse is taken with a star product and the second one is usual inverse. So, in particular you can do another inverse. So, K will be like D normal inverse times D inverse with a star structurally.
Just to suppose it wasn't star convolution, but ordinary convolution. Then take ordinary convolution with the derivative of a delta function. That convolution produces derivative of the operator. It's not very surprising.
So suppose your D was the ordinary, just single derivative.
Ordinary convolution. So a function of one derivative. A convolution is f of x minus y
times
times that g of y. Now let's choose f to be derivative of delta function. Do the integral over y. It will produce g prime of y.
Yes.
So it's not, in ordinary convolutions we could always represent derivatives by convolutions with some specific functions.
I see.
It's not too surprising you can do the same with star convolutions.
Yes. And in particular this operation will give an explicit expression if you want.
Okay, but these functions that you star convolute with are nicer than the delta functions. So it smooths out.
But we can see the partial T and then the mass in the last line of K.
Sorry,
It's like the Fourier.
these two?
Yeah.
Yeah, so all this complicacy is in the space part. So this is like the time part which has no complicacy and this is like the constant part. So they don't have any complicacy. These things are also very nice in some sense. I can tell you what this operator is. This operator is nothing but this, the inverse of gamma mu p mu plus mf.
So fun. I mean, getting the integral equation is hard. But solving it was. But getting the integral.
So when we were in zero magnetic field case, propagator was this gamma mu p mu plus mf. This was my solution when I am in momentum space. Now what you have to do, you need to take an inverse but using the star. This quantity is just that.
Literally, I think in half an hour people will start leaving.
Okay, let me go fast. So basic point is that, so the basic point is that we have converted the whole equation structurally in the same way, like all part has a star convolution and then we want to use star inverse to solve for it. So everything is written in, so here is the equation when written in terms of this variable. K starred with alpha is an identity, therefore you can use the inverse of this operator star operation and write alpha in terms of K, which I am doing here. Alpha is written in terms of K. So now K is in particular the free part plus sigma. So I have replaced alpha in terms of sigma. This is the solution of first equation. Now we are coming to the second equation. Second equation is sigma in terms of alpha. What we want to do is to write down alpha in terms of sigma using the previous slide and we want to solve this equation. Again from this equation we make some algebraic observations, and these algebraic observations say the following, that only two particular components of sigma are non-zero, some plus and identity, some very specific algebraic statement which is not very important. What we do is that now for these functions we expand into this coefficient E and M's, and this is supposed to be an equation for those coefficients. So earlier we had an integral equation over one variable, now we have an summation over one variable. So all this happened is that you had integral equations, they became summations. Earlier we used to solve using the differentiation, now we will be solving using differences. This is the structural part of this. Okay. Now first we already make the observation that sigma was independent of omega in momentum space. So all omega dependencies are known in this equation. So you can in these equations involve an integration over omega. So you can do omega integral. Okay. So here I am writing things down so that this omega integral is easier. So this omega integral is supposed to be done over a contour in which imaginary part of omega is I times mu. Mu is the chemical potential. So in general that's how you want to do the integral and get the equations. But first I will be explaining when mu is 0, how to go about it. Okay. So what one does is that one does all these integrations over omega and get some equations. These are the difference version of these equations, which are pretty complicated. These are coupled nonlinear difference equations, which we are supposed to solve. Here I have defined a quantity chi n, which is a particular combination of poles of the propagator, which will turn out to be very important for solving some algebraic function.
And those poles themselves were functions of the sigmas.
Yes. So if you know of the chi's, yes.
And therefore, I mean the poles, the zeta pluses
Poles, yes.
were functions of the sigmas. So the right hand side also depends on sigma, but are very complicated.
So your propagator was written in terms of self energy. In particular, poles of the propagator are functions of self energy. Now this equation says that self energy is a function of poles, but in other words, if you know all the poles, then you know the self energy. So that will be a consistency. So these are some algebraic equations and we solve them by defining this some function in, and all these equations become this simple recursion relation. In minus 1 is some 4. Then you solve in. Once you solve in, from this equation you solve this particular combination I kept calling chi n.
This was a miracle done by.
Okay, so you solve for chi n, and from these equations you see you can, these are the difference version, you can write the summed version that will involve summation over chi n. So you can write down the solutions in terms of sum over chi n. Now in this equation, notice this is a one term recursion relation. So the lowest term is undetermined, some undetermined constant, which I will be calling Cf. So everything can be determined in terms of this undetermined constant Cf. Recursion relations are one term recursion relations, the lowest term was undetermined, which I am calling Cf. Now using those equations, everything is written in terms of one unknown quantity Cf, and here is the solution for poles in terms of Cf. Cf squared 2b times n plus 1, n is an integer, runs from 0, plus minus lambda f times b. This is the solution for poles depending on the integer n, depending on coupling lambda f and unknown constant Cf, which we will determine in a while. So now we turn into this poles and rewrite in terms of a variable, which was Landau level. So earlier when we did free theory calculations, we identified our n with this Landau level parameter. This is some algebraic relation. So we kept it in mind and we rewritten this spectrum in terms of this physical variable nu. And what happens is that it exactly takes the form that we promised. Like it has the free part nu plus half, it has this 2b times s, 2 is the Landau G factor, b is the magnetic field, s is the particular spin depending on lambda f that we defined, and Cf plays the role of effective mass. Now this is the spectrum we were hoping for. Now we want to solve for Cf. So Cf is solved by what Siraj said, that you have all the solutions in terms of Cf, but in particular your poles were defined in terms of those solutions. So that gives you a closed equation for Cf. So we will turn into this equation, but now I am turning on chemical potential and want to see what kind of changes happen. So chemical potential shifts the contour. Whenever a contour moves past a pole, that changes that equation a little bit. So you can solve this, you can get these equations and you can solve them. I am directly presenting the solution for them. Here I am assuming energy levels up, so chemical potential is here up to positive energy band m is filled By field I mean chemical potential is above them. These are positive energies and then there are negative energies. So, I am assuming chemical potential is here and I am presenting a solution for them. Capital M is the level up to which the levels are filled. So, things that are not filled, they have exactly the same spectrum as earlier. Here zeta exceptional is this. So, there was this bands given by N and there was one floating around. So, this floating around pole is called zeta exceptional. This is nothing but a particular quantity written in terms of CF. So, the part which is not filled remains unchanged and the part that is filled behaves like a free particle with effective mass zeta exceptional with no interaction with the magnetic field. This is like a free fermion without any interaction. So, we have levels which are filled, which are like free fermions, we have levels which are unfilled, they are like anions. This is the picture and in between you have some joining conditions.
So where is the broadening?
The second part I have no idea why.
So the
Yeah, so broadening.
universe is to be broken.
Yeah, so far we are looking at the levels, we have not looked at the broadening of the levels. We will define what we mean by broadening and we will give an expression that will have.
That would be the L dependence that is going to.
Yes, yes. In the degeneracy level that will split. Yes, that will be the L dependence. Yes, yes. So we will come to that. Here I am just presenting the equation satisfied by this undetermined constant. It's a equation which needs some regularization, but the regularization that was anyway needed. Yes.
The things which are filled, where are they in this equation? N less than.
Yeah, these are the levels which are filled. N less than equal to m are the filled bands.
Why do you say B drops out from them?
B drops out. No. I am saying this is the
what drops out from them from the field level?
B dot S coupling.
B dot S.
So these are fermions in a magnetic field.
They behave like they have spin half.
Yeah,
They
yeah.
Not like the shift in the spin sort of goes away.
I
Lambda F dependent.
is going away. So yeah, I have no idea
That
why.
goes away for the minus sign there also. What does that mean?
Yeah.
That anyway is filled, you're saying.
This is unfilled.
So
This one is filled.
minus sign that they cancel.
They will cancel. Yes. So the spectrum of free part and spectrum of
Minus is also free.
Yeah, that's what it is.
they yeah, depending on your chemical here I am taking positive chemical potential for this example. So this negative bands are also filled in some sense.
So when you say anions, you mean if I excite the system so that some electron pops out of this field C and goes up to one of the unfilled levels, that behaves like an anion?
That will have a phase factor, non-trivial phase factor.
Yeah, and certainly at least it's a spin of the ion.
Yeah, I mean, I was just saying, so this is like the Fermi C. And suppose I have a quasi-particle excitation, that would behave like an anion.
That will be.
The quasi-hole would behave like an ordinary electron.
Yeah, somehow makes no sense, right? And maybe we're saying that wrong.
I have.
Is that the statement?
No, I didn't think that was the statement. Is that?
Feeling.
Okay, maybe we should just talk about this excitation on top of this.
Yeah. Yeah, it's so strange.
I thought what you were saying was that if you start from deep inside the form.
Yeah. Sorry, are you going to re-express this in terms of mu?
New.
In the new variable? In terms of
Yes. So this part in terms of new variable will be the expression A here. This will just be this expression.
And that works for any value of n larger than mod n, right?
Yes.
Both positive and negative.
Both positive and negative.
So it's these funny bands that behave special. So suppose your mu equals 0, both the particle and the whole behave like they have the right spin. But it's the bands that were filled and their negative counterparts that behave.
Negative counterparts because they are equal in this case.
I don't know why. I really don't know.
No
To
idea.
go to the same extent below.
Once you go below and down,
Down.
Sorry, what did you say?
Your gaps, your mu is between the Landau levels, right?
Yeah, let's say the mu is from the mth to the m plus 1.
Mu is positive and between m positive band and m plus 1 positive band. Then the special ones are positive m bands and negative m bands. So up to minus m, these are the special bands. Below this you have minus m minus 1 band, they are like same. So it's this, if your mu is here, then these are the bands which are special. The positive ones that are occupied and their negative counterparts.
Everything above is because normally as
If I understand right, if you added a particle, so you have filled up to m.
yeah.
Yes.
If you added an extra particle in m plus 1, that behaves as per norm,
No, like it.
right? And if you create a hole,
Mm-hmm.
that means you take something from below and put it up.
Or just take something from below.
So if you just take something from below,
If you take something from below m plus 1,
then
then
it's fine.
It's fine. But in this band, they behave fine. It looks like, at least all we have is the energies. We don't have anything about the dynamics. But the energies behave like they're just spin off.
That's what you.
Yeah.
If you excite it small enough, it would be fermion and an electron. I mean, whole.
At least in terms of
It
energies.
seems like that.
At least in terms of energies. At the moment we don't really have any dynamical information. And maybe just the interpretation of that as being free fermions is not right. I don't know. This is just the result of the energies.
Yeah. Now we come to this issue of validity of this calculation. To do the calculation, we assume that there are no pole on the integration contour. So we assume that mu is in between two levels. This is sort of the assumption that went into this calculation. So we are asking the condition when this is valid. So here I am defining the condition for which this is valid. Let me draw a picture that will be like sort of easy. Suppose you have a particular band in free limit, now that broadens out like this. Then this approximation of assuming this band is filled is true as long as your chemical potential is up to the top of the band, and the assumption that this band is not at all filled, that assumption is true as long as your chemical potential is no larger than the lower part of the band. So this upper part we define to be mu up and this we define to be mu down. The value of chemical potential, the lowest value of chemical potential for which it is consistent to assume mth band is totally filled, this is mu up, and here I am defining this quantity which is mu up minus mu down. So this is, if this band was really becoming wide, broadening up, then this quantity is supposed to be positive in this example, and so this will have very interesting information. I will come to it, how to interpret this, sort of like we have some ideas about how to think about this. So this is the quantity which we want to calculate.
Maybe you should just say that mathematically once, just to make it totally clear. That mu up is the lowest chemical potential for which it's consistent to assume
Mth band is totally filled.
that the mth band is filled and the m plus 1 is not.
Okay.
And mu down is the highest chemical potential for which it's consistent to assume that the m minus 1th band is filled and the nth band is not.
Yes.
And because we have different gap equations depending on whether you're here or here, these two mu's are not the same. So because they're not the same, you get a gap. This thing white.
Now we come to the interpretation of this gap, how to think about this gap.
So you don't actually see the energy levels as poles being
Broadened out.
No.
We just, we do the calculation here, and then we see that there's a range where technically speaking we cannot do that.
So there are some interesting suggestions by Siraj, like for example you can take the residue, some part of the upper, some part of the lower when the pole is on the line, but he has the comment that it might not be the correct picture because maybe the large N approximation is not valid when things are on the inside the band.
I have the strong feeling, there is this analysis by Suk-Sik Lee, which tells you that the large N flavor business breaks down when you study fermions. This is the thing that made him famous. That a large NF expansion breaks down the study of vertices, and actually instead of bubble diagrams contributed, planar graphs contributed. I suspect that something else, something like that will happen when we're within that. There's an interesting thing, but we just leave it for the
Yeah. So that part we have no idea how to deal with right now.
Yeah. And it shouldn't be so simple because, you know, the single particle picture should break down inside the band. It's too easy, too simple. And you can't get interesting physics.
Yeah. So now suppose
It's interesting that it works even in the range it does.
Yeah,
The
you can
same-
surround the problem. Yeah.
And what would the expectation be for such?
See, if you change mu to say 1/3 filling, Vikram would tell us we should see the 1/3 filling quantum effect. So we should see that, you know,
Which band though?
and every
Any.
we should see a very intricate structure within this.
And you mean you should see the fractional
Quantum.
quantitative. But I mean, it's not clear that you would see it with Chern Simons interactions, right? I mean, you get it for some real world interactions. I mean, Coulomb. Right?
Coulomb. But I mean, does it
You
depend
said
very
that
sensitively?
it's a very robust.
But if you get it with this, then that would be cool, right? So probably the first way.
Right. But I mean, you know, there's no proof that
There's no
any
proof and
interaction
there's
of
no
whatever
reason
kind-
to expect that Chern Simons is the right interaction.
So what was the thing that shows up?
That's all.
This was what. Yeah, I should say that we started this project because Ashwin encouraged us to look at it.
yes,
It
yes,
was
yes.
really cool.
He gave this sort of the idea, do it.
So the thing that he did was without magnetic field.
Well,
Was without magnetic field, right?
the thing that we did before was. After a talk I gave at Harvard, he said, can you do the same thing with magnetic field? Because, you know, suppose you can solve it there, wouldn't it be nice?
Okay.
Okay. So now we are considering this width of the band when this is greater than 0.
So within this broadened Landau level, all states are delocalized, meaning they're extended.
It's a good question. Actually, really speaking, technically we have no clue what happens within this. Now we can then solve the equations making various ansatz. You know, because we've got everywhere in between we've got a pole of the integration contour. We can break it up into fraction f above, fraction 1 minus f below and solve it, and we get an answer. But we have no real understanding of what the right thing to do is there. So at the moment we're just not making any statements about that. I don't know. I suspect that something very interesting is going on now. That, you know, if you do my ansatz, the one that Indranil also mentioned, you will get a continuous spectrum. But I suspect that the true answer is that there's sometimes mass camps. It's maybe as interesting as QCD. You know, like really interesting physics. And whether we have any control over it, I'm not sure.
So what I was thinking intuitively in terms of was that often like when you have these Chern Simons kinds of theories, often these fluctuations of the gauge fields mimic the effect of quenched disorder in many systems. And we know that if you take 2 plus 1D problem and you have just static disorder, not fluctuating in time, then the Landau levels do broaden. But not all states in the Landau level are delocalized. So
There's a middle range that's
Yeah.
right, and outside that's not, right?
it's gapped, yeah.
Yeah.
And then the very broadening of these Landau levels and the fact that they're not infinitely sharp allows us to actually see the quantum Hall phenomena. Otherwise we wouldn't have seen it.
So when you hit the delocalized states,
Yes, you have a bunch of delocalized states, there's a mobility edge, and then you have localized states.
where you see the platoons.
Yes, yes, yes. So that's what I.
This is with Chern Simons interaction? This
With
My intuition is that this plays a similar role
yeah.
as the fluctuations of this act as some background disorder. Although it's fluctuating in time also, so it shouldn't be exactly the same.
We'll come to you for a tutorial about this if you don't mind. You know, part of the problem is we're totally
So this is also related to the so-called NBL problem. There is some kind of a belief that you can have many body localization conditions without having explicit disorder. And in almost all such cases, I have seen that there are some fluctuating gauge fields present which kind of act as some disorder. And in the quantum hall problem disorder does lead to broadening of Landau levels. And so only the middle few states remain delocalized and giving it a mobility edge. But this is a totally different kind of mechanism, so I have not much intuition what's going on here. But if there is a mobility edge, some states in the Landau level are extended and some are localized and gapped out. That would be really cool.
I hope we can access it.
So, right now we will discuss what this difference, this widening means. So, if it is positive, then it is sort of obvious that this is the width of the band that we are considering, but the interesting fact is when it is negative, how to interpret it. So, when it is negative, then it is saying the following, that the energy that you are needed to put an electron at the top of the band, like when the last electron of the band is mu up, that is lower than the energy that you need to give to put the first electron in the band. So, suppose you have this system and you are increasing your chemical potential little by little. The moment you reach this mu upper, then this band has the probability of going directly a first order change and going into a situation when the band is completely filled, because this is the lowest energy state compared to filling the band by one single electron. When mu up is lower than mu down, that means the energy needed to put the last electron in the band is lower than putting the first electron in the band. So, as you change your chemical potential, the moment you cross this mu up, you have this chance of filling the band completely, like abruptly. So, this will be like a first order change.
Yeah. Maybe you should say at the technical level, one sign means there is a range of energies where we have no reliable solution, and the other sign means there is a range of energies where we have two reliable solutions. There is a competition. He is giving intuition for which the competition.
And you sort of expect this picture to be valid when the particles that you are putting in the band are interacting in an attractive manner, so that their interaction sort of lowers the energy, so that when things are filled, then it is lower energy than when things are not filled. So, this is sort of the intuition for this. And now, I will be presenting an expression for this gap calculated in a perturbation theory. So, we have this interaction strength lambda f. So, this is a perturbation around lambda f equal to 0. This perturbation theory is a first order perturbation theory, but from numerics we will see this is very good approximation. Even for lambda f is almost like half. So, lambda f takes values from 0 to half, but it is a very good fit for that. And then we have another perturbation theory near lambda f equal to 1. This is a strongly coupled point of view from fermions, but this is weakly coupled perspective from the dual bosons. So, we can do a perturbation theory in bosonic variable, which is lambda b. So, in both ends we have these results. First I come to this part.
And maybe you should say, Indranil, it may not be clear to everyone, that while we can do everything analytically, there is one thing that at arbitrary lambda f we can't do analytically, that is solve for zeta exception. So, one equation for one variable, it's a horrible equation, we don't know how to solve that equation. So, that you have to do numerically and generally.
Yes.
What was zeta exception? The
C.
The unknown
So,
constant.
all that we are doing here is solving for that CF in perturbation.
And putting those answers back in the energy levels and calculating the difference. Now, I have some graphs, let me show the graphs. So,
This was
all
all at 0 temperature.
at 0 temperature.
We have not touched finite temperature.
Yeah, so, all the 0 temperature calculations, and in the x axis we are plotting the magnitude of lambda f. So, this is the fermionic end and this is the bosonic end, and on the y axis we are plotting various energy levels in the units of magnetic field. So, here I have 4 graphs. First, the solid lines. Solid lines are plotted numerically. So, here it is written, the blue one is for the upper chemical potential, and what is this color? This is some grey color. So, this grey color here is for the lower part. Here we see from the numerical graph that near lambda f equal to 0, the switch happens. The switch is the one in which you have the mu up is less than mu down. the one which was sort of associated with the phase transition. So, near lambda f equal to 0 they are different, but at lambda f around this around 0.5 they switch they cross each other. So, here you have a band which is widening up, and it happens at a very strongly coupled regime from both the fermionic and bosonic end, and we do not have a like any analytic calculation here. Numeric shows this, and here what we have plotted this in the dotted lines, the results that we get from lambda f perturbation theory. So, they match quite well up to some 0.4 or 0.5 for lambda f, and then they deviate.
The dotted lines are what order in lambda f perturbation theory?
The first order in lambda f perturbation. Yeah, it's amazing, and actually we can do it up to like 4-5 orders if you want analytically. It's not hard. This perturbation theory we can improve.
Just to understand, close to lambda f being very small, is the ordering here because symptomatic of attraction between the fermions or repulsion?
Yes, so
Just to
so near the band it's attractive,
It depends on the relative sign of lambda f
and if the intuition is correct, then near the band,
B.
but
If B is positive, it depends on the relative sign of lambda f. Sign lambda f positive or negative shows difference.
yes, but for this particular sign where I have taken lambda f to be positive and b to be positive, this is the signature of being attractive near lambda f equal to 0, because this is the case when there was this first order transition. Now, they have very nice behavior as you change signs. I can draw these figures.
what I wanted to ask was if you took, is this a reasonable way to ask the question? Like, maybe not, but if you took two of those particles, could you have to compute something to see whether they are attractive or not?
Well, we
Yes.
computed the S matrix before, but the point is the magnetic field is playing a very important role.
Yeah, magnetic and also chemical potential.
That's right, yeah. So, I don't really know.
Essentially in lambda f perturbation theory, the quantity that determines this is the spin and magnetic field interaction. This b dot lambda f determines it. Other interactions are subdominant. Here you see this is 1 minus something, and the quantity that is determining this sign is lambda f times b. So, if you take b to 0, then okay. So, this has some features. So, first of all it has a crossing at a very strongly coupled region, and you could have played with the signs, and then in certain cases, for example, if you have taken lambda f to be negative, then this crossing will not happen. From the beginning they will be separated and they will remain separated. That I am not showing, but these things are there. Now, I am showing the same for the same sign the graph in lambda b perturbation theory. So, this dotted lines are lambda b perturbation theory, supposed to be good here near 1. So, here they are sort of meeting with the numerical plot, but then they deviate. These are like 0th order perturbation theory around lambda b. Now, 0th order is already interesting, because as you can see this is increasing without bound. So, you have a UV cutoff, but so it is going like near the UV cutoff. So, it is like this is the so I am showing you an answer which is valid for a field level. So, I have already filled some of the energy levels, and I am trying to go near the bosons at 0 temperature. So, we know from free bosons, if we had a free boson, then if we take chemical potential and make it larger than the mass at 0 temperature, then Bose-Einstein condensation happens. So, this is like the signature of that in interacting theory. For first of all, it is interacting because it is critical boson, and second it is interacting with Chern Simons, and as we go near this point we are basically turning off the Chern Simons interaction. So, this is supposed to be a statement about ungauged critical boson theory at chemical potential which is higher than the lowest level. So, you take ungauged critical boson theory, put it at a magnetic field, make your chemical potential larger than the lowest level, then you see that this is sort of sign of the condensation.
And in particular the ungauged theory, it blows up.
In particular, if you are strictly at lambda b equal to 0, then this is like going to infinity and 6 sort of, but if you turn a little bit interaction with the Chern Simons, that sort of regulates it. So, at here you will probably see here, but as you go nearer and nearer to this bosonic end, it diverges. So, an interesting point here is that can we do the same calculation with the condensed boson picture?
I'm just a little confused about something, sorry. So, it's the and you have a chemical potential, and the blow up, but you don't have a bare mass at least, right?
We could.
But suppose you didn't have it, just for a moment.
This we
Then
have.
the theory would have been conformal, etc. And now you turn on a chemical potential.
First a magnetic field, then again.
First a magnetic field, and then a chemical potential. And then when do you get the Bose-Einstein condensate?
I just have one comment to make. Taking mass to 0, here I am measuring everything in the units of magnetic field, that is like infinite magnetic field. So, first of all these calculations are, let me keep little bit of mass if you want, like all these calculations are strictly valid, like concretely valid if I take mass to be something but non-zero. Then you are taking massless limit of this theory. So, it might not be the same thing as making B equal to 0 and taking massless limit.
Okay. I was just trying to keep the number of different scales small in my mind. But
I don't think qualitative
matters.
You know, you've got a Landau level. When you take your energy, when you take your chemical potential above the first Landau level, then you have trouble.
Then it condenses to that level, sort of.
That's all it is. But I mean,
I know. I mean, I wanted to be precise.
okay. But I mean, since it's an interacting theory because of the 5-4 potential.
Yeah, you might have thought that would cure it, but it doesn't. You need the lambda. Everything diverges. You know, the free boson theory, of course, we know it diverges.
Yeah, but I just wanted to.
Yeah. Here also continues to diverge. It would actually be good to have a qualitative explanation. The thing that cures it is lambda.
So one can do this calculation in the critical boson theory.
Except they're going to get infinity. I mean, what we did, if you just set lambda b equals 0, okay, good, no, good question.
So, we will come to this, we will come to this.
Good question.
So, one hope is to do the calculation from bosonic end and see. So, first we try to do the calculation when the bosonic end is not condensed, in which we can do the calculation reliably and we reproduce the answers from the fermionic end under the maps of duality. That serves as a check of the duality or correctness of our calculation. Okay. Now, you can ask the
giving some mass and then tuning the chemical potential to less than that.
yes, less than that. Now, you can ask what happens from the bosonic perspective if you try to do the same calculation with uncondensed theory. What you will see, you will run into mathematical contradictions, because you are supposed to do the same calculation using condensed theory, which will be W boson and G boson picture. See, here the potential is very steep. We are in the critical boson limit, where the potential is very steep. The potential which gives the vacuum expectation value for phi. So, either it is 0 or it is a condensate. Now, when we are doing the calculation, we need to make sure around which vacuum we are doing the calculation. If you try to do the calculation around 0 condensate,
Which calculation?
you are trying to take critical boson Wilson-Fisher theory gauged with Chern Simons, and you want to do calculation around phi bar phi equal to 0. This will be called uncondensed calculation. Let me define it like that.
For some value of chemical potential.
So, some value of chemical potential. Now, if you take that chemical potential to be larger than the pole mass of the theory, if you do that, then from the bosonic end this uncondensed phase calculation gives you inconsistent results. So, what you are supposed to do is to do the same calculation, but around the vacuum in which you have a non-trivial value for phi by phi, which will be the condensed phase calculation, which we have not tried in this paper, but something that one should do and check what happens.
In the absence of the magnetic field in a paper we wrote about a year ago, we checked that this works beautifully.
Yes.
Again, this W boson.
So, take the magnetic field to 0 and then take lambda f to 1, then you are and do perturbation.
And take the bosonic mass to be negative. Okay. That will force the bosons to condense. And fermions give you a prediction, but we can reproduce that whole prediction.
But fermionic prediction is just infinity.
For turning on a chemical potential. In the previous what we did, in the absence of a chemical potential, just negative mass, right? Okay, it all works beautifully.
And at 0 magnetic field it worked like anything.
Yeah. Now we haven't tried the analogous calculation.
So, I mean, just to understand, the analogous calculation could be that you take a mass if you like, but you take the chemical potential lower than that, keep lambda f equal to 1,
Yes.
and look at that as a starting point.
That we have looked at already.
And first of all, do you get the condensation?
No, you kept chemical potential less than mass.
This is a bit of a question. I don't know.
So, sorry. Why are you keeping it less than mass? Then you are not supposed to condense. So, sorry, you are giving more than, right?
Maybe he has NB.
I meant the other way.
Oh, sorry, you meant the other way, yes.
Other way around. But I thought there first you want to check, you get a Bose-Einstein condensate, then you turn on lambda b.
Yeah, I think we do get a condensate because, you know, suppose you assume there's no condensate, then we do some Gaussian integrals. And the sign of the Gaussian in one of the two switch, in one of the integrals we have to do, turns positive instead of negative, which is telling you that it's going up.
Because this chemical potential is shifting the mass.
Exactly at that point. So something is happening, but we haven't seriously thought about doing that.
Okay, and then I guess the point is you assume that there is a condensate. But
Yeah, you have to do it with that assumption. New vacuum, expand around a new vacuum. Yeah, yeah. So in the absence of magnetic field, we did this, works very good. But we have not tried it.
No, but with the magnetic
absence of magnetic field, presence of chemical potential.
Yeah, absence of magnetic field.
But keep chemical potential less than the pole mass, then we have checked it.
You have checked it again.
Yes.
It works nicely.
It
Yeah,
works
it's
nicely.
Consistent
Yes.
condensation story.
Yes, yes. But when you take chemical potential larger than mass, those calculations are still valid. You haven't studied them very carefully.
Yeah. One more comment. When we turn on a temperature, we did the whole calculation in the presence of temperature. When you turn on a temperature, nothing very special happens when the chemical potential goes past
Yes.
the pole mass. So there you can analytically continue around. But here we're stuck at zero temperature where something quite dramatic happens at this point.
Maybe I have a comment about charge.
Okay, go on.
Okay. So in these theories,
So we need to work basically. We don't really.
so if you try to calculate charge as a function of chemical potential at some finite temperature, so you plot, you give a value of lambda b, some coupling constant, then plot charge as a function of chemical potential. It looks something like this. It has a non-analyticity. So this is the point where, so given lambda b, this is the point where the pole mass is hitting chemical potential. So your pole mass is determined in terms of chemical potential, lambda b and temperature. So you are giving lambda b and temperature. For that you are solving for the condition when the pole mass is almost mu, that is this value, let us say. Then if you plot your charge as a function of chemical potential, there is a non-analytic growth around this point. This is like, this growth will be sort of related, has the length of lambda b, log lambda b with a c. This is the dimensionless mass. So if you go to 0 temperature, this you should particularly put a factor of beta here to get the dimensions. Then it will diverge. So this is the analog of Bose-Einstein condensation. At 0 temperature, at lambda b equal to 0, you have Bose-Einstein condensation, and this is sort of the regulated version of it. You put finite temperature, go to a lambda b, then you still see some non-analyticity. We don't understand it very clearly.
Yeah, I'll just say to Arvind, I believe that even in the presence of chemical potential, while formally we can do the calculation, I haven't completely understood it. At least I feel.
Yeah,
No matter what the chemical potential is for lambda and equals 1, it seems to, what kind of predictions one gets from fermionic theory?
Yeah, what this is saying, at least at the moment, is that the Landau level energy is divergent. This is what it's saying, right? This zeta exception is going off to infinity, pole mass is going to infinity. What it tells you is that there's some very sparse, if you take a continuum limit of that, it tells you that the density of states is becoming extremely sparse. But you know, that sparseness may not be a problem, because you see the density of states of the bosonic theory should be controlled by NB. Whereas the density of states of the fermionic theory is controlled by NF. And precisely the ratio NB by NF is lambda f by lambda. So it may,
In the right variables,
it may be telling you that it organizes in something okay. I just don't understand
in the MB.
NB. I think just at the moment these are the results. What exactly it means in the bosonic, at least from my point of view.
yeah.
It just needs to be.
What is E along the E over root P along the y-axis? It is the, what exactly is that?
So this is this square. The square root b is just the scale, and E is the value of the pole. So, it is the energy which will Lorentzian signature will be the energy. Which
So let's say this is the first filled Landau level. How its energy is behaving as a function of lambda. It's diverging. That I think is true. Exactly what it means, I don't completely get.
And where is the chemical, okay, so if some finite value mu, it diverges.
Keep that chemical potential always above the first. When you do the calculations, so the chemical potential is above, let's say, the first Landau level.
Yeah.
Now, since this is going up, we are also scaling.
And E is the energy of what Landau level?
Let's say the first. Was this which one did you?
Oh, so you keep the, so when E is diverging, mu is also diverging.
Yes.
If it's above.
Yes.
Oh, I see.
it is always kept above this.
You want this to be filled.
You want this one?
You want it to be filled. But note, Indranil will say the gap also diverges. The width of the Landau level also diverges. But all the divergences we see from lambda b perturbation theory are 1 by lambda b. So it's not just a random divergence, it's a very particular divergence. Which is the same note, is the same as NB by F. So it may have a very simple interpretation.
Mass square, ratio of mass square will the gap squared sort of, the squared goes like 1 by lambda b, otherwise it goes like square root, right.
No, but the poles are the poles, right?
Yes.
2-point function.
Yes.
Issue of scaling it.
No, yeah, that I agree. So poles will scale like 1 by square root of mod of lambda b.
Yeah. So in the chemical in the magnetic field problem, these energies just do diverge. But in the zero magnetic field, all of these energies get grouped together into a continuum. So the divergence here just tells you that the density of states is becoming sparse. Okay. Now the ratio of the two density of states naively seems to be NB by. Because the gaps between them are scaling like 1 by lambda b, which is the same as NB by. So the original density of states was NF times this, which sort of looks like it's replacing it by NB. So it may not be, you may not see such a dramatic effect in the zero magnetic field. You may just see NF being replaced by NB. I don't know if this is correct. I just made it up here.
And you're saying you haven't done the zero magnetic field case.
I mean,
Not
but
well enough
we've not
to know.
understood that part. I mean, in our paper we had a little subsection on chemical potential, the formal section. We didn't think much.
We didn't write this charge calculations there. We
Yeah,
didn't.
just didn't think about it.
That time I also went home. You remember?
Yeah.
And
But now this is very strong motivation to understand
yeah.
the chemical potential where the field goes up. Okay, so
Yeah. So this is what it is. Finite temperature in the bosonic language, and this is this in the middle of the band. These are the three sort of futures directions which one want to understand.
But just wanted to ask you, at the moment, can one ask whether you get the Landau levels, but just go back to what Vikram was asking. That per se does not show the plateaus, right?
In the middle, the plateaus. Which ones you are asking? In the sorry, I didn't understand.
Like the free theory in a condensed matter system with no disorder or nothing would not really show the
plateaus in Hall conductivity.
the Hall conductivity.
Would we see it? Actually, I just don't know.
Yeah, no, that
Might
would
just
require but just to ask another question, because after the free energy work, you folks also analyzed various endpoint correlators, right?
Yes.
And what about the retarded current correlator?
To get the conductivity?
Yeah.
Yes.
And that's a key correlator here, right?
Yeah.
You'd want to do that as a function of chemical potential when you were in the lab, right?
Yeah.
The main thing is that we don't, that we could make an ansatz.
But
That's all.
even outside, how did this look?
Yeah,
Like when you're
even
outside the
that
band,
is
still you can have some interesting structures
Yeah.
or not.
Yeah, then you should just see the quantized one.
Yeah, integer, you might.
Integer. That
But
integer.
even that would be very interesting. See, because that would show that you have localized states.
That's interesting. Yeah, that I'm pretty sure we could do.
This we will be able to do for sure.
And then that's great.
The propagator is there, you need to analytically continue and then get that.
You will do JJ though, so it's
You have to do
side
JJ
side.
And
The loop, whatever the gap analog of this equation is more complicated.
Much
but you
more.
guys have managed to solve
we
it.
managed to solve it with q plus equals q minus equals 0, q3 non-zero.
Good enough.
That might be good. I think because you're interested in this JJ correlator and like a zero frequency, right? I think it'll be good. I think that we can settle.
That would be great.
Also, I was thinking about if one can think about the higher spin theory. So now we are turning on a magnetic field. What happens to the conservation law? So earlier it was divergence of J was JJJ.
Yes.
That equation used by Maldes and Zhuvaydov to solve for the 3-point functions. Now, what is the structural feature of this equation? Can one say anything? Can it be used to do something? Or pure Chern Simons with a background magnetic field, can one do some calculations?
Pure Chern Simons? What is it? How do you couple it?
Yeah, so you do A OH B.
Oh, I see.
Yeah, so you keep one of them background because the equations of motion will sort of set the.
But
So-
just for the U1 part.
No, say you have an UN Chern Simons coupled with, so I will write down the Lagrangian. Suppose A is the UN connection, you take the trace of A, which is the U1 part, and you couple it to, let's say dB.
But then isn't it like the U1 theory coupled to the magnetic and the SUN is
Yes,
different?
yes,
So it's basically just the U1 part story.
yes.
But that's probably figure. It's just an A wedge dA plus A wedge dB, right? Then
And what do you want to do with this theory? You
Yeah,
want to
yeah,
put
yeah.
these
So,
lines?
yeah, I want to put Wilson lines and see the magnetic field dependence.
completely expectation values, huh?
Yeah, can you do or like
That must have been, that's not done.
What do you want to compute?
sorry. You are doing it purely in the this part, right? Are you doing purely in the U1 part? I am not integrating over
The
B.
Wilson lines carry charge in the both. Huh? That's what you want to do.
Yes.
Okay.
So there is non-trivial magnetic field dependence. And how-
It's sort of interesting because now the equation of motion for the U1 part of the dynamical gauge field will tell you that dynamical field strength plus V is equal to charge.
Correct.
It sort of changes that.
But can you do these calculations? Because for pure Chern Simons, all these things are done.
So what in pure Chern Simons exactly what calculation? you
So
do?
if you had pure Chern Simons, you could have calculated the Wilson loop, expectation value of Wilson loop in S3, for example.
Maybe it's more natural to do S2 tensors.
Yeah.
Because you have magnetic field.
Yes, I agree. S2 cross S1.
You
Then-
put a bunch of operators. And previously what you got is number of conformal blocks.
Now what do you get here?
Now what you get.
And also, did you tell Sandeep about this index idea?
I am.
So I should tell that also. This is sort of also in that direction.
Any chance you're coming for lunch with us in the
I have to go to faculty today.
Oh.
If I come a bit late. Yeah.
So if you take the index in n equal to 2 Chern Simons on, let's say, S2 cross S1 and put a background magnetic field, you can still maintain the BPS configuration.
I see.
And what happens is that this background magnetic field sort of acts like mass of the excitation. Now if you take the magnetic field to be very high, that is like you are making them very massive. And first of all, you are making them massive, and also the high magnetic field localizes the wave functions just from scalings. So like very high magnetic field is like you are taking particles, localizing them, not making them interact much. So, you expect your answer to simplify in this limit,
I see.
and then can you do a perturbation around b equal to infinity?
So you want to take, you want to just take Chern Simons, say on a sphere or something, let's say, and then compute with the magnetic field turned on the Witten index. Or
That is already calculated. We just need to take that answer.
and take that limit, but to get what then? I mean,
You have this background magnetic field turned on. You have to do it in a coordinated manner to do the BPS to maintain the BPS configuration.
I understand that.
And then in this coordinated manner you calculate the index at finite n and k, for example. To simplify it, let's do large n. So you have an answer. This answer is complicated. It's not just Wilson lines with the WZW model fusion rules. It's more than that.
And then the final answer you want to compare with WZW to understand it in terms of the CF.
Yes, yes. Can you do that? So magnetic field going to infinity limit is like making them Wilson lines. I don't know how precise it will be, but this is an idea.
Interesting.
Okay, thanks a lot.